Hello everyone. Today we will talk something about the ammonia measure. Everybody have heard the term laser, isn't it? Laser refers to light amplification by stimulated emission of radiation. And here in measure, the same thing. We have, instead of light, we have microwave. Microwave are also electromagnetic waves traveling with the same speed, the speed of light. Now today, before going into the practical utility of this quantum mechanical wonder, we will first go deep into our previous lecture, in which we discussed something about the ammonia molecule and its states. We referred to the ammonia molecule and assigned only two states to it, two states of orientation or rotation in this tetrahedral lattice. We are seeing it right now. Here, and we connect those by bonds. Bonds are actually electron pairing, which have other deep implications in quantum mechanics, but we will not go into the issue, and we will describe this as a chemical bond, just as a chemist describes it. And we have this plane of hydrogen, and over it tetrahedrally a nitrogen molecule is situated. So we have this state, and we call this state number 1, and we'll go to state number 2, in which we'll look at it differently. This will be like the same thing. See, the nitrogen molecule will come over here, and the hydrogen 1, hydrogen 2, and hydrogen 3, I guess. Yes, they will be again in a plane. They are not moved, only the nitrogen is flipped over. So we have the second state. So we have two states, the first state and the second state. They are congruent, and if you match them, they will strike similar. Only they have changed the orientation of the nitrogen molecule. Okay, now what we have written previously is something like this: IH cut dc1 dt is equals to E naught c1 minus ac2, and IH cut dc2 dt is equals to E naught c2 minus ac1. So these were the problems, and we had solutions of this, and I will give the solutions as it is prepared right now. First of all, I will give the solutions, isn't it? In a state, say the ammonia molecule is in the state 5, it can be described as C1 times state 1 plus C2 times state 2. So C1, C1, what we know is that C1 is equals to 1 bra psi ket, and C2 is equals to 2 bra psi ket. So we'll go further into the explicit expressions of C1 and C2, which we had done previously, but this is of prime importance in today's discourse also. So this goes C1 equals to a by 2 e to the power minus I by h cut e naught minus a. Mind it, e naught minus a, something less than the base state energy which we have considered, plus b by 2, take this as b e to the power minus I by h cut e naught plus a into t. Mind it again, here it comes as e naught plus a. So there are two terms which oscillates at two different frequencies. First one with this frequency and second one with this one. I think everybody is familiar with Euler's notation that e to the power I theta equals cos theta plus I sin theta. Now C2, what will be the terms? C2 will be a similar one, but with a slightly different perturbation. See, here it will be minus b by 2 e to the power minus I by h cut, and floating state obedient to the stream. So everything rest remains the same, but we want to have some states with definite energy. See, the states are not of definite energy, they are of two different energies. See, two different energies we can ascribe to them, but how to ascribe a single energy to a state? So we'll go to what we call superposition of states, or let's see, now we'll use Roman symbols. We can also use other symbols, but we use Roman symbols as it is given in Feynman lectures, is equals to C1 plus C2. If you use this, then see, b by 2 cancels here, and the total term that comes over has only one dependence of E naught minus A, isn't it? So this gives us a state. Which has only a single energy dependence. Okay, then but we are entangled in a problem here, that if this goes likewise, then what will happen? Yes, we can write this, say, to abstract it out. See, from this we are abstracting out is equals to 1 plus 2. Stop singing. 2. So now we have the same thing. We can write in bra notation, 1 plus bra 2. Yes. Now if you multiply, that means this is just like a scalar multiplication. We will have 1 1 1 2 1 1 will give you 1, and 1 2 will orthogonal will give you 0. This one will give you 0, and 2 2 will give you 1, so you will get 2. So this is not legitimate for a state. It is taken for granted that that it is taken that once anything is in this state and we are calculating the amplitude of this going to this state, the similar state, then the amplitude will be plus or minus 1 or anything which e to the power something which in the probability, that means this thing square will give us must give us a value of 1. So in order to do this, we introduce 1 by root 2 over here and 1 by root 2 over here. If we do this, then this thing will come over as say 2 and 2, and this thing will finally come to be 1. So if you square 1, you will get the normalized function. Okay, so we have finally given one state. A state is given by this thing. So another state will be given likewise similarly by this thing equals to 1 minus 2, likewise 1 minus 2 by root 2. So this new set of state, first we had this state 1 and 2, and we are now pursuing another other states, Roman states, which are more suitable to us in mathematical procedures. For there is a dependence on the energy of the system, which is a solitary one, a solitary dependence on the energy of the system. Now with the previous equations and manipulating these equations and using C1 plus C2 is equals to C1 plus C2 is equals to C Roman 2 with root 2 sign, manipulating this will get another form, and it will be a standard form. C Roman 1 dt gives E naught plus A into C1 minus is equals to E naught plus A if we take this to be E Roman 1 C1. So you can see the wonder, the spectacular behavior of the evolution of the state. For this is a much simpler equation than the previous two one. In a similar manner, we have IH cut d C Roman 2 dt is equals to E naught minus A C2 Roman 2. This gives us, if we call this E Roman 2 C2, then we are almost in heaven. Now this is very easy to calculate from here what will be the Hamiltonians. See, first of all here C1 carries a coefficient of E Roman 1, then H11 will be equals to E Roman 1. H12 will be equals to 0 because C2 is not there, and for this thing this will be H2 1 and this thing will be equals to 0 and H2 2 will be equals to E2. So this completes the Hamiltonian matrix of the thing, and from this from the stationary states, now what we have found, the stationary state, why do we call it stationary state? For they carry the energies, they carry the energies, single energies, so these are stationary state. What are stationary states? States with definite energies, and they vary. In which manner? If you solve this equation, you can find the varying character, and it is equals to, say like this, C1 varies as e to the power minus I by h cat. Nothing new, everything as set up. We stand on the shoulders of giants. This thing will be C1 equals to, in this manner, and so we have the pair of bases, the base Roman 1, the base Roman 2. Now from the differential equations which had been set up before and manifested in our own language, we get that this thing, that C1 we have introduced it before. This from the equation gives us e to the power minus I by h cat E naught plus A by A times T. Okay, now and this is a stationary state, isn't it? This is a stationary state. We are considering that anything is in this state, so the amplitude of finding the thing in this state will be equals to 0 for their orthogonal. Then C2 must be equal to 0. Okay, and similarly, if it is in this state, if the particle whatsoever is in this state, then we will have C1 equals 0 and C2 will be equals to e to the power minus I by h cat E naught minus A times T. Okay, now if they were in a mixture of states, then we would have this C1 this and C2 this. We wouldn't have 0, but we have 0 here because we are considering pure states. Then for pure states, we know that the time dependence, say phi Roman 1, will be equals to, say it was first in Roman 1, then it would be in Roman 1, and its time evolution will be minus I by h cat times E naught minus plus A by A times T, and psi 2 is equals to 2 times e to the power minus I by h cat E naught minus A times T. Do you recognize that here we have a lower energy. Here have a lower energy, and this will be a more stable state. So with such considerations, I will end the discourse here. But as we have written C1 and C2, will write any function, state vector, sorry, in the form that it can be written as this thing, or it can be written as this thing, this in Romans. End of the day. See you in later lectures.